Okay, so back to our notes. So we want to use this equation, and we need to talk about this moving direction D. But what is this moving direction D? Before we talk about this moving direction, I'm going to introduce something called the conjugate direction. Okay, so it's something very new for you. So we define this conjugate direction. Okay, we define this. Actually, conjugate directions, a lot of directions, but they are conjugate to each other. Okay, so I believe the following description of conjugate direction is the key to this method. So I'm going to spend a little time writing down the derivation. So given a symmetric matrix X, Q, I'm sorry, and two vectors D1 and D2. Okay? Then we say D1 and D2 are so-called Q orthogonal. If D1 dot Q, actually there's no bracket yet, Q matrix dot D2 equals to 0. Okay? That's how you describe something related to conjugate directions. Okay? And we can also say, or we can say D1 and D2 are conjugate with respect to Q. That's another way to describe Q orthogonal. So what does Q orthogonal mean? Q orthogonal, the mathematical way to describe it is basically here. D1 dot Q dot D2 equals to 0. Or in a more easier way to describe it is D1 and D2, they are conjugate with respect to Q. Okay. Actually, for us, I think the math is more easier to understand. The wording are just wording. You don't truly understand it. So basically, there are two vectors. When they follow this kind of rule, you can say they are conjugate. They are conjugate, and they are they follow this kind of rules. Okay, and before we move on, I would like to invite you to focus on one thing. Let's think about negative, actually inverse Hessian dot negative gradient. Let's think about this. So in the past, in Newton's method, this is the key that takes us to the optimal. And over here, there's a matrix having a dot product with a negative gradient direction. And we know negative gradient direction is the descent direction. the direction that goes down, descent direction. So from here you can see negative Hessian is trying to help to change the direction. So this is a key to change the direction. And actually, the length of the vector. So inverse Hessian is very powerful. Not only it knows which direction to go, but also it knows how you can change the length of your movement. You don't even need a coefficient in front. When we use steepest descent, we need alpha, a coefficient in front, because we don't know how far we need to go. But in Newton's method, there's no coefficient here. Hessian inverse itself already know where to go, because it was derived from the second order Taylor's expansion. It was derived from the first order derivative equals to 0. If you watch my video in the week that we don't have class. If you didn't watch it, please go and watch. Okay? So now, from here you can already tell a matrix having a dot product with a vector. This operation can help you to change direction and also sometimes change the size. So how about here? It seems like another thing to think. Can someone tell me, are D1 and D2 orthogonal to each other? The answer is yes or no. Are D1 and D2 orthogonal to each other? Who say yes? So who say no? Because someone say no. Okay. So the answer is not necessary. Because they could be, but that doesn't need to be. And for most of the time, maybe no. You didn't say the dot product between them equals to 0. But their only chance to be orthogonal is that they are perpendicular to each other. So if they are not, the answer is no. So for most of the time, D1 and D2 may not be 0. Right? The D1.D2 may not be 0. So when it's not 0, that means may not be orthogonal. Right? But there's a rule right here. We have this very important rule. D1.Q.D2 equals to 0. So it's some kind of orthogonal. So we call it Q orthogonal. And what does it mean? The way I memorize it, or trying to understand this, is like this. I always think of this as the following. I always have a feeling that Q is the matrix that makes a transformation on D2. So D2 is being transformed, being rotated, and maybe being scaled. Once D2 is being transformed into a new vector, that new vector is orthogonal to D1. So you can say Q is like a transformation matrix. And D1 and Q dot D2 are orthogonal. So that's how I understand it. Okay, and this idea is very important for conjugate gradient. Because over here, sorry, I move up and down. We want to find two vectors. They are Q orthogonal for conjugate gradient method. So they are not regular orthogonal. They are Q orthogonal. Okay, so that's the key. So they don't need to be orthogonal to each other, but they are Q orthogonal to each other. Okay, so that's the important information about this method. Okay, so once you understand this, we can start to talk about what we want to do. And let me see, where do I start? Okay, so here's the first step. Okay. In steepest descent, we have, from now on, our notation will have a lot of bracket and the index number, iteration number. Later on, I may simplify them. Let me see if I simplify them right now. Okay, so from now on, this means this. Okay. Sorry. Because if we keep using this uppercase bracket K, it's going to be a lot of this bracket and K. So I'm going to simplify this. Okay? So in steepest descent, we have x k plus 1 equals to x k, and we have minus alpha k gradient f k. That's what we did. And let's rewrite this in the way we want to do it for steepest descent. So we rename this as our positive dk. So at the end, we have dk plus alpha k, and of course it's a vector dk right here. Okay, we rewrite steepest descent in this way. So we can now try to plug in some numbers. Let's take a look. x1 actually equals to x0 plus alpha 0 plus d0. Okay, and let's advance k by 1 and plug in again. You can see x2 will equals to x1 plus alpha 0 and then alpha 1 d1, right? What if I plug in the first equation to the second one? Then I know this definitely is x0 plus alpha 0 d0 and then plus alpha 1 d1, right? I basically plug in this guy to this guy. I just plug in. So did you see a rule? Optimization is always like the original design here, original design plus some kind of moving direction with a coefficient in front, plus another moving direction with coefficient in front, and continuously adding those terms until you feel it's optimal. Okay, So linear optimization methods, actually they are not linear. I should say the gradient type of methods, because we are moving along the gradient direction. They kind of follow this kind of formulation. Okay? So from here, if I keep on doing this until I find the optimal solution, then I know my optimal solution definitely looks like this. My optimal definitely look like this if I stop at the k iteration. Okay? So this is, I think you should be able to understand, right? So, in order to help us derive this whole thing easily, we can consider one thing. We consider this to be 0. We just consider x0 as 0. Okay, I think that's fine. We can start from the origin. That's fine, right? It's easier for the later discussion. And also, because we would like to, again, for our discussion, we renumber those index. So this is so-called the index, right? Index. We are going to renumbering the index. It's okay. It's just a number. Oops. So what we get at the end is alpha 1 d1 plus alpha, and this time we say we stop at index n. Okay, just changing the symbol for k. Okay, just renumbering. Okay, so over here you can see there are n different di vectors. So it's like, where is my optimal solution? It's somewhere starting from the origin, and I'm going to move n times. Every time I move along a di vector. And for every movement, I will move by the size of alpha I. Okay, so that's a concept. If we derive starting from the beginning up to here, it should be easy to understand. Optimized gradient kind of method is like this: move along D1, then move along D2, move along D3 until you move along the N and you stop. That's your optimum, right? Okay, so if you understand this, now let's try something. We're going to do an operation, and this operation is a dot product. So let's do a multiplication. Okay, so it's a dot product in the front. So what we are going to do is we do a dot product of d1 dot q dot in front of everything. So this is our operation in the front. We are going to apply this at the front of every term in the above equation. So let's try that. So because alpha 1 is a scalar, we can bring to the front, and we keep the vectors at the back. So we should have something like this. And this is the exactly same operation, right? Okay, we did the same thing to every one of them. Okay? So now what do? We make an assumption. We assume D1 to Dn are Q orthogonal. We assume they are Q orthogonal. So what will happen? Can someone tell me what will happen? Yeah, many zero. We get a lot of zeros, right? Good. So if we have this, many of them are zeros because we said, let me remind you. If d1.q.d2 equals to 0, it's called a Q orthogonal. These two are Q orthogonal. So how about d1.q.d1, but with itself? It's not 0 because it's the same vector. Okay? But when we talk about Q orthogonal, we are talking about two different vectors. And when we apply Q transformation on one of it, that one, the result of that one will be perpendicular to the first one. Okay, so these two are called the Q orthogonal. Okay? So in this case, we said D1 to D2, they are Q orthogonal. Then the above equation will be reduced to D1 QX. This is not 0. This one, alpha 1 D1 dot Q dot D1. No more. The rest are 0 because the rest, they have this Q orthogonal 0. Right? Everyone okay? So what's amazing is that we now can determine alpha. Every time I see this, I feel like, who invented this method? Who think of this method? How did they come up with this idea? So it really amazed me when you see something like this. Okay, so since you have this, alpha 1 is just a number. So we can determine alpha 1. If you know D1, if you know Q, and if you know X star, you know about alpha 1. It's interesting because before we talk about this, we never tell you how to determine the alpha. Alpha is like how much you move along that direction. We never tell you. But now we do. From this assumption, as long as D1 to Dn, they are Q orthogonal. I feel very interesting. So this is one important equation later on. How come this is not the end? Because we don't know X star. We never talk, because the goal is to find X star. In this equation, it's impossible for us to know the optimal. If we know the optimal, it's not necessary to do optimization anymore. So obviously, this is not the end. And also, we never talk about what is Q. Okay? So, this is first part of the derivation. This will be utilized later on. Now we need to do a lot more of derivations and then put everything together. So let me see what we need to do next. Okay, the next thing that we want to do is we are trying to replace this guy. Okay? Because we don't like x star in our equation. We don't know x star. So we are going to find a way to replace this. Okay, so the next one, trying to replace q dot x star. Okay, so how do we do that? We need to follow, we need to recall the second order Taylor expansion. Okay, so what does it look like? We have, of course, a objective function, and the Taylor expansion looks like this. Your function will be close to another function where you have a expansion point. This is your expansion point. And you will have x minus x0, they are vectors, dot product gradient, plus 1/2 x minus x0, dot product Hessian matrix, plugging in x0 times this. Okay, this is your second order Taylor expansion. Okay? I think it's very important to memorize second order Taylor expansion for optimization, because it is the most fundamental equation for almost not every but lots of methods. Okay, so as an optimization engineer, I think it's important to memorize second order Taylor expansion. So please, if you can, try to memorize it. It's not very hard. Okay, and for the following derivation, again, we are going to make this everything simpler. Otherwise, it's a lot of writing. So over here, we're going to rewrite this as so there are several steps. We just consider H as our Q. It's like let's try to do that. Okay? Nobody say Hessian must be our Q, but let's try to consider H as our Q. Okay, so what else? So over here, let's look at this part. We will have 1/2 x dot q dot x. Right? The one in pink basically is right here. Okay? And what else? We will have a lot of the first order terms. So one of the first order term is right here. This is first order. And we also have some first order terms inside the right hand side. But basically we have some first order terms. Let's combine all the first order terms. So the pink part is right here, and the yellow part, and also it's difficult to write to highlight the first order terms, and also the first order parts in here. We can combine them together. We can say they are called a B vector. We just call this negative B vector. Okay, so all the coefficients in front of x, we just combine them together into a B vector. Okay? And how about the rest? You can see this is like a constant. This is a constant. And also we have some other constant terms. These two multiply together, that they are constant terms. And also these three multiply together, they are constant terms. Okay? So all the constant terms, they're just numbers. So that's just plus C. These are the rest of the constant terms. Okay, just combine them together, just a number C. Okay, once we have this, remember we always want to make sure our optimal is found at first order derivative equals to 0. So we want to have gradient f equals to 0. When we have this, we have optimal. Okay? So what does it mean? That means right here, when we do a gradient operation, at the end, what we get is this: q dot x minus b equals to 0. Okay? And we believe when this satisfies, we believe our optimal satisfy this equation. Okay, so this is what we believe. Our optimal point, if we plug in this equation, this gradient should be 0. So if we can do that, that means we can also plug in to the right-hand side. Right? This is what we believe. So our optimal should satisfy this equation. Okay? And let's go back to see what we want at the beginning. We want to replace q dot x star. Now we have q dot x star. So it seems like choosing Hessian as our q is a good choice. Right? Right here, we said maybe we can consider Hessian as our q. But we didn't know if it's a good choice. Now we feel like, oh, it's a good choice. So I should consider Hessian as my q, so that I can use b to replace q dot x star. Okay? So let's keep this one. Copy this and paste it here. So, sorry, only I can do copy and paste. You need to write it again. Okay. So this becomes what? This becomes d1 dot b and d1 dot q dot d1. Okay? And actually, I should not say q. This is h at the end. Because we already say we are choosing Hessian as our q. Okay? So it seems like we kind of get rid of x star in this equation because we don't know where x star is. But we should be able to know where is b. So maybe we can go back and see what is b. So what is b? So from the Taylor expansion, the b, we said negative b. Here should have a gradient vector here. Right, we should have one term right there. And we're looking for all the first order terms. So we should have something like 1/2 of x0 dot Hessian 0. Actually, two of them. So the other one is 1/2 Hessian dot. Oh, so two of them, they're the same. So actually, just minus Hessian 0 dot x0. Okay, so the b vector, it came from our second order derivative, second order Taylor expansion. If you really want to know, b can be derived from there. But we don't need it right now. That's okay. But if you really need to know, like I said, what is gradient at 0? It's a gradient at your expansion point. And x0 is your expansion point. Hessian 0 is the collection of all the second order derivatives at the expansion point. Okay, so it's basically the combination of gradient and curvature information at your expansion point. Okay, so they are something that you could know if you try to calculate them. Now, even we have this new equation, it seems like it doesn't help us to find the optimal yet. So we need to actually do more. Okay, so what do we do? Let me see. So the next thing that we should do is we can really try to solve by what we know so far. So now try to do some trial formulations. Okay, so what we can start, even though we have some equations from steep conjugate gradient, it's not yet something that we can handle. So in the first iteration, we can start from steepest descent, because steepest descent is something that we know how to do it. So x1 equals to x0 negative alpha, and actually, it's fine. Let's write it again. Okay, this is our steepest descent. And following our new notation, we are using this d vector, d0. Okay? So d0 is negative gradient 0. So this is something that you will use it later on. I just write it down here. Okay? And as the iteration continues, you will have some k iteration, and at the moment you have your design point at the k iteration minus your alpha k, and actually here we can directly use this d notation plus alpha k dk. Okay? So we can kind of we want to try to define dk. Let's try to define dk. Okay? So let's say, how about, because we really don't know dk. Even though we know, we wish every d is q orthogonal. But remember, q is our Hessian. If we use Hessian, that means we're using Newton's method. So how can you not use Newton's method but still follow q orthogonal? Okay? So since we try to define dk, there's a way. We kind of follow steepest descent. We kind of follow it. Follow steepest descent. And here, let's say, how about dk equals to negative gradient fk? But I know if I do this, I'm still following steepest descent. Right? This is basically steepest descent. So for conjugate gradient, I'm going to introduce a new movement. So the new movement is going to be plus beta k minus 1 dk minus 1. Okay? So this is newly introduced to dk. So we still try to evaluate the gradient. This is the negative gradient at kth design point, right? And this is newly introduced to dk based on previous dk minus 1. Okay, so we newly introduce dk minus 1. We newly introduce a move direction to dk. So if we do that, we don't know alpha k, we don't know beta k minus 1. But if we can figure out how we can determine alpha k and beta k minus 1, then, and if we can figure out how they are so that it's following Q orthogonal, then it seems like a plan. Seems like a good plan, okay? So, how do we do that? We have a wish. We wish every dk is following Q orthogonal. Actually, H orthogonal. Because H is our Q. This is what we wish. But we don't know yet. We wish. Okay? This is basically H orthogonal. We know if they are H orthogonal, eventually you can find your optimal solution. Okay? So, in your second order Taylor expansion, you have your if f k plus 1 almost equals to your fk plus, maybe I do it too quick. I need to copy the previous Taylor expansion here. This is Taylor expansion. In Taylor expansion. Okay, in Taylor expansion. If I call this xk plus 1, and if I call this xk, if I do that, then my equation becomes fk plus 1. This is like a simpler way to write. Fk plus, this is going to be xk plus 1 minus xk dot product gradient fk plus 1 half xk plus 1 minus xk dot product hk. Oh, they are vectors. These two are vectors. Dot product xk plus 1 minus xk. Okay? If I just call my x as xk plus 1, and I call my x0 as xk. And also, now we're starting to play some tricks. Let's take a look at this one. This equation tells us xk plus 1 minus xk equals to alpha k dk. Right? We know this. Then we can kind of replace many terms inside our second order derivative. Okay? Right. So we have fk plus 1, fk, and here I have alpha k dk, dot product gradient fk plus 1 half. Here I have alpha k dk, dot product k, dot product another alpha k dk. So 2 alpha, so alpha squared. right? So this is one step. And like always, when we have a second order Taylor expansion, we always want the first order derivative equals to 0. So again, we want first order derivative equals to 0. We want this. So, but this time, we don't derive in this way. We actually do a partial derivative with respect to alpha k, because alpha k is something we don't know. It's also a variable. And even when we, like, remember, along the line search, we are keeping alpha as our variable. So everything is known. And we are trying to determine what is the optimal alpha. Here is the similar idea. Okay, we want to determine alpha. So we do a first order derivative with respect to alpha. Okay? So I can actually write first order derivative. Let's do that. So when we do that, we found at the end we have dk gradient fk plus alpha k, and then dk. This is what we have, right? And we wish this to be 0. Is it? Yes, we wish. This is what we wish. Because along the line search, before we truly, we don't know alpha yet. So if we find an alpha such that the first order derivative equals to 0, then that alpha must be the alpha that we're looking for. So that equals to 0 is what we want. Okay, so right here we are going to rearrange something here. Here is a dk in the front. Here's another dk in the front. So you can take that out of everything. So you will have something like this. Okay? You have something like this. Okay, so from somewhere we can get something similar to this. So where? From here. From here. Actually, not here. From this one. From there. If we do a first gradient, let's see what happens. If we do a gradient, what we get in the end is gradient f plus Hessian times your x k plus 1 minus your xk. Okay? If you do a first order gradient, if you apply a gradient. And this is basically your alpha. This is basically alpha dk, right? Remember this guy. So this basically is gradient fk plus alpha, this is alpha k, Hessian k dot dk. Then you will see they are the same. Exactly the same. So what does that mean? That means this equals to dk dot gradient f k plus 1. Okay? So now we have what we have. dk we have something like this. Okay. This is going to be used later on. Okay. So it's a very long derivation, but every step is very simple, but you just don't know why, who has this kind of brain to, follow this kind of math and do a lot of derivations like this. Okay. So I think it's a good time for us to recall what we have done. Sorry, maybe a little small. We try to do some trial. At the beginning, we are trying to do some, sorry, a little small. Do some optimization, right? And then we start from steepest descent. We start from steepest descent. Okay? And once we have, we start from steepest descent, as the iteration advance to the next iteration, advance to the kth iteration, we should have an equation like this. Right? But we don't know what is dk. We define something called alpha, something called beta k minus 1. So this is something we define. Then we wish every dk is h orthogonal to each other. So right now we are trying to achieve that. We are trying to make every dk h orthogonal to each other. So whenever you don't have a trick, usually second order Taylor expansion is the trick. So we begin with second order Taylor expansion. We apply this equation to second order derivative. We try to do first order derivative with respect to alpha. We also did gradient. So basically first order derivative with respect to x. And both we wish them to be 0. So this is so far what we did. But remember, what we try to do is to make sure all the d, they are h orthogonal. Basically, this is the idea. But so far, not yet. We are still having a distance from making sure they are h orthogonal. So let me see what to do next. Okay, since we are dealing with all the dk and dk plus 1, so let's recall what is dk. Where do we have dk? Here. This is where we define our dk, right? So let's make a copy. This is our dk. So let's recall. This is our dk. And if k advanced by 1, what does this equation look like? Basically, negative f k minus 1 plus beta k dk. If the index number increased by 1, this is how it looked like. Okay. Now we are going to do a post multiplication. Multiplication. Okay? Of what? Let's see. We do this, and we do a dk here, and another dk here. Okay? So this is the operation, the post multiplication that we did. And we do the same thing on every term. Okay, we do the same thing on every term. Now, remember, we wish every D are H orthogonal. So this should be 0 because of H orthogonal. So the other two, they are not 0. And from here you can tell we now can calculate beta. We can calculate beta. Right? So actually, if you use this in the equation earlier, you can find the optimum. But you will be using Hessian. If you are using Hessian, that means you are using Newton. Okay, so this is the beta where combines the power of Hessian, but utilizing a line search approach to find the optimum. So let's go back. What happened? Sorry. We started from steepest descent, right? Here we have steepest descent. And we don't know how do we update our moving direction. So we define a new moving direction. And inside this moving direction, we define a new coefficient beta. We don't even know what is beta. But at the end, when we derive several things, if we wish dk and dk plus 1, they are H orthogonal. This is a way to make them H orthogonal. Just use your beta k like this. Then you can make sure every dk is H orthogonal. Then you should be able to find your optimum. But inside this definition, you still have your Hessian. This is something we don't want. At least we now know what beta k look like. At least we know this. So the following step is trying to replace Hessian inside this beta. So in the following, trying to replace Hessian in the beta derivation. When we do achieve that, that means in our optimization we never need to calculate Hessian, but we still can have some kind of ability to update the direction of D. And we can make sure our new direction is H orthogonal to the previous direction. That's the beauty of conjugate gradient. Okay? being able to move along H orthogonal direction, but you don't need to calculate Hessian. So the beauty is being able to move along a new direction, for example dk plus 1, which is H orthogonal to dk without truly calculating H. So actually this is what we wish this algorithm can achieve. Otherwise, why do we need to derive so many math? Okay? So please understand why this method is being derived in this way. Now, when we trying to replace all the Hessian in beta, we are going to talk about the upper part and the lower part of beta separately. Okay, now we talk about the upper part. Okay, so the upper part equals to gradient k plus 1 dot Hessian k dot dk. Okay, I'm just copying down. Now, we need to kind of rewrite this whole thing and see what happens. Remember, dk came from this. Right? dk came from this equation. So we know dk actually equals to this. Right? So we can actually plug it in. So just plug in. What happened after we plug in? We have a alpha k at the bottom, and we have gradient f k plus 1 Hessian, and we have x k plus 1 minus xk. Okay, we can do that. Now, we have seen this multiple times, right? Hessian times xk plus 1 minus xk. We have seen this. So let's take a look where. Somewhere above. Here. We have seen this, right? This where did we get this? It came from the gradient of second order derivative. Okay, we have that. So let's copy it. And paste it here. So since we have this, so we can also plug in. So now what do we have? Alpha k gradient f k plus 1. Now we should have gradient f k plus 1 minus fk. So what's interesting is that the upper part no longer has a Hessian. Disappear. Hessian is being replaced. So that's the trick, how you can get rid of Hessian. Okay, and let's rearrange this. Alpha k here, gradient fk plus 1, gradient fk plus 1, minus f k plus 1. Just expanding those. Okay. Now, we are going to do something with the second term. Why is that? Let me see, why is that? Why do we need to do something with the second term? Because we have to. Because second term equals 0. We have to do it. Okay, but we need to prove why the second term equals 0. Here, the second term. We want to make it 0 because it's 0. Okay, the second term. In order to make it 0, you need to do this. Only the second term itself here. You need to rewrite the gradient f here. So using which one? Here we are going to use from the definition of dk. From the definition of dk. Here. This one. At the beginning, we already defined this dk. I feel like the person who invented this method, he's playing puzzle. Just plug in here, plug in there, see what happened. I don't know how he did it, but he did it. Okay. So from here, since we have this, so we can we have a gradient f right there. So here I can rewrite as negative, here, beta k minus 1 dk minus 1 minus dk. Okay, just plug in. Another plugin. Okay. So after the plugin, let's expand the whole thing. This basically is this. And here is beta minus 1. Okay. There is a very important equation that we used earlier, right here. Why did we make a box right there? Because it's going to be used right now. Okay, from there, from the notes earlier, we already derived dk dot product with gradient f k plus 1 equals to 0. We did that earlier. Now it's being applied. The same thing. Dk dot product with gradient f k plus 1. We know it's 0. Okay, so the second term now only has this this left. Okay. Now we want to make this whole thing 0 as well. So how do we make it 0? We need to do another recall again, another recall and plug in. So let's recall which one? Let's recall gradient f. Recall this one. It's right here. Recall same one here. We're going to use something about this over here. So we know this guy, it's actually alpha k dk, right? This is alpha k dk. So we can just plug in the entire right-hand side into this equation. So a huge plug-in. So once we plug in, what do we have? Beta k minus 1, the whole thing, just plug it in. Gradient fk plus alpha k Hasium k dot dk, and then dot dk minus 1. Now expand the whole thing. Beta k minus 1 gradient f k dot dk minus 1 plus alpha k minus 1 beta k minus 1 alpha k Hasium k. This one you need to reverse it. So here is dk hk dot dk minus 1. Okay. At the end, you have something like this. So for the multiplication between these two, you need to reorder them in this way. So you can do a vector dot matrix dot vector. Okay. So, because Hasium is symmetric. Now, remember, since gradient fk plus 1 dot dk equals to 0, we know if we minus the index by 1, this should still be correct. So we know this is 0. Right? And how about this? This is definitely 0, because this is H orthogonal. So with all these efforts, we are just trying to get rid of this guy at the top. The entire second term, basically. Here, the entire second term basically is 0. We spend so much time just expanding it, plugging in different kinds of equations we have, keep on expanding until every term is 0. Okay. So what is this? This is my upper part of beta. So now we know the upper part of beta is right here. So let's just bring back and take a look. Upper part of beta here. So at the beginning, we have an upper part of beta. At the middle, we have Hasium. With a lot of derivation, now the upper part of beta has no Hasium. Only with 3 items. Alpha k, gradient f k plus 1, dot product with the same thing. Only these. So I think the interesting thing about this method is that how did he keep on rewriting the equations and then found an easier formulation? It's so magical, right? So when the first time when I learned about this method, I have the same feeling like you. When does the derivation is going to stop? It's taking so long. It's too much. How did this mathematician figure out this way? Okay, I have the same feeling. But once you just trying to follow it and realize, oh, this term can be replaced by this, then you will, I hope you will be amazed by the derivation. So actually in probably 30 or 40 years ago, there is a lot of researchers are doing this. And there's a group of people, they are focusing on the research about sensitivity analysis. So sensitivity analysis basically is a lot of derivations regarding to derivatives. Okay, and they are trying to find an easier way to do sensitivity analysis. And from here you can tell they are doing such a good job replacing some terms related to gradient with simpler formulations. Okay, so I hope you are you could appreciate what has been done, so you don't need to do it. Okay, now get back to the lower part. We are done with the upper part. We can handle the lower part. So the lower part is right here. The lower part is right here. So what should we do? We actually, before we just work on this, we should plug in the upper part back to beta. So let's copy the entire beta. Copy. Paste. So when we plug in, we know we have this guy. So here. This is our upper part. So let's plug in. This is our upper part. But here. I'm going to move this alpha k to the bottom. So we have alpha k here, and copy the whole thing. So this is my new lower part. Okay, so let me not call this guy lower part. Sorry, I'm going to get rid of this. Sorry, if you already wrote lower part here, please get rid of it. Let's call this guy lower part. Okay? So now we want to do something with this lower part. What should we do? Let me see. Okay. In order to do this, we are going to start from this guy again, this equation. From that equation. And I'm going to copy it right here. dk dot. Okay, I need this from over there. Okay. So once I have this, I'm going to do a post multiplication. Pre-multiplication, sorry. So this time, use dk. So we do that on every term, multiplying every term. So why did we do that? Because this is our lower part. Exactly the same lower part. Exactly the same, right? So very good. We found a way to get rid of Hessian. And again, this guy is 0. If you remember here, dk dot product gradient f k plus 1 is 0. Okay? We already, it's right above right here. It's right here. Okay, we already derived earlier. I made a box. I forced you to made a box. I told you it's important because it has been used multiple times. So we know this one is 0. And the lower part can be replaced by this new thing. So now beta k basically can be rewritten as and what? Minus dk dot fk. Okay. Right? But we can even do better. How do we do better? Or why is it not good? Why can't we stop right here? Because right here you have some information about dk inside. And what is dk? You need to go back to see our formulation. We very early here, right? This is where we need our beta. So we want our beta to be constant. We don't want beta to have something that we don't know. Okay, so dk is like something that you cannot just directly calculate. Gradient you can calculate just by finite difference or calculation. But dk is having, what is dk? dk is having a long description. dk is this. dk is long. dk has a lot of terms. So we don't want to use dk inside beta. So that's why we ask ourselves, can we do even better? Okay? And actually, here is a good chance to recall the original definition of dk when we define beta inside. So we are going to recall that one. Oops, I didn't. Okay. So let's recall this one. When we recall this, we figure out what can we do? Just directly plug in. So now this can then be negative gradient fk plus beta k minus 1 dk minus 1. Just directly plug in. Dot product with gradient f. So this equals to plus fk dot fk minus beta k minus 1 dk minus 1 dot gradient fk. Okay, what is this? This is 0 again. Why? Because we know since dk dot gradient fk plus 1 equals to 0, if I minus the index by 1, dk minus 1 dot fk, of course, also 0. So what do we have at the end? We have a very simple formulation. So this is the final equation. Finally, I should write finally. Beta k equals to gradient f k plus 1 dot gradient f k plus 1 gradient f k gradient f k. Or when we need beta k minus 1, our equation is gradient f, just minus all the index by 1. How simple is this? Okay, so how did we got this? There's a lot of plug-in and some assumptions. And let me remind you, if we use this, what does it mean? You start from steepest descent. And then whenever you advance your iteration, you try to move along a new direction. You wish your moving direction is h orthogonal to each other. So you newly define a new direction. Inside this new direction, you introduce a beta. You don't know how to calculate beta, but you wish this beta will help you to make sure your moving direction is h orthogonal to each other. Now you finally found this beta is the beta that makes sure your new moving direction is h orthogonal to all the other moving directions. And based on the concept at the very beginning, we believe if we can move along many different directions and they are h orthogonal, at the end, I can find the optimal solution. Okay? So that's how this method is being derived. But I believe even up to now, you still don't know how to use it. You just see a complex equation being derived into even more complex formulation and magically become a very simple equation. But I need to tell you how exactly you can use it. So here, the following is the key, how to use it. The flow chart of conjugate gradient. So if you have no interest about any derivations about today's lecture, just read the following. Forget the above, okay? But if you find the above are so fascinating, you're like me, then you can join me. Okay, now, always start with a initial guess and iteration number k equals to 0, right? This is the same. Now, we need to calculate the gradient. Oh, I am going to use the simpler way to write it. Okay, so now you calculate gradient. So in conjugate gradient, you don't need to calculate Hessian. So what's next? You have your iteration equation. Okay, so here's the main procedure of conjugate gradient. But over here, how do you get alpha? Can anyone tell me how do you get alpha? 2 words. Actually, there are many solutions, but can anyone tell me how do I get alpha? This guy. Say again? You can speak louder? So what would be the procedure? Line search. Yes, line search. We still need to calculate alpha, but we don't know alpha. Line search. So I'm going to write down the subproblem. So once you have this formulation, you need to send to a subproblem. So over here, you are minimizing f of alpha. And once you found your optimal, you then update. So your alpha k equals to the optimal of your subproblem. Okay? Then back to our problem here. You will do a convergence check. And if yes, your optimal is your last design. If not, go back. And k equals to k plus 1. So that is conjugate gradient method. So before you see this is the same as steepest descent. When k equals to 0, your moving direction is your negative gradient. So in the first iteration, basically you are doing steepest descent. But starting from the next iteration, you advance to this procedure, and when you try to determine your moving direction, you need to use this one. And this one basically is negative gradient plus some update on your previous direction. And combined together, this is your new moving direction. So you have your new moving direction here, but you still don't know the alpha. So use line search again to determine alpha and check if it's optimal. So this is conjugate gradient. Okay. What time is it? I think it's about time. You need to do a homework. And then next week we have an exam, right? Do you think you are okay with it? Do you need one more week? Okay, the problem is 2 weeks from now, hold on. Two weeks from now, April 1st. April 1st. Is it a holiday? April 1st is a holiday, right? So if you don't do exam next week, you will see a holiday. Then you are in April 8th. So what do you think? Should we postpone 1 week? Postpone, because I feel like you may need some time to practice. How about this? Next week, I show you some programming about these methods. But you know, I already have the code. So my discussion, my introduction to my codes is going to be very fast. Do you want me to write the code from scratch? Yes. Even I do that, it's very fast. But okay, let me try it. Next week, let's try some coding about these 3 methods in MATLAB. Okay? And you can also use the time to learn about MATLAB. And of course, every time when you program, if you didn't directly copy from somewhere, it's always going to be having some bug. So you can also experience how I debug. Okay? Then I may ask you, how about this? We do a larger homework. Since you have 2 weeks, I think it will be good if you do a hand calculation and also try to do some coding. It's okay if you use MATLAB, like me. I can even share some code with you. Or you can try to find your own platform, like Python, C++. I think Python is a good tool to use, because Python is even simpler than MATLAB. So let's do a homework. Please minimize. I think this time we can do a third order, because conjugate gradient is going to converge maybe in 3 iterations. Very fast, very fast. Don't worry. My favorite number. Try to solve it until it converges. I think you can converge very fast. Maybe 3 or 4 iterations. Okay? Try to solve it. But using conjugate gradient. Okay? Try to solve it. It's a lot of fun. And if when you use this method and you found your iteration is going crazy, that means you did something wrong. Okay? That happens. Because sometimes people, when you guys try to calculate this, you get the wrong number. And you will move along a totally wrong direction. Okay, try to solve it and find programming platform. Like MATLAB, C++, C#, Python, or anything that you are good at. I'm only okay with MATLAB, a little bit Python. I'm trying to learn Python. I download an app to learn Python, but I forget to use it. So I already waste a lot of money, but I'm still learning Python. But it's very easy. I feel like Python is very easy. I know some C++ and C#, but my students actually are better than me. I hope. Okay, so please try to figure out a way to program some optimization algorithms. Because later on, when you do a research or do a project, probably you can use it. Okay, that's it for today. See you next time. Oh, by the way, so next time is the coding lecture. Okay, if you want, you can bring your laptop. You can follow. And my coding lecture, I'm going to use MATLAB. Okay, and then is a holiday. Then is exam 1. So I'm going to tell you what's in exam 1. Basically solving optimization by Newton's method, steepest descent, and conjugate gradient. By hand. Okay, by hand. So if you didn't do your homework, you will see a problem. So solve it by yourself. It's okay if you have friends, have discussions, but don't copy. Because you need to experience it. Sometimes you need to practice to master those methods. Otherwise, in the exam, you just don't know what to do. Okay? See you next time. This exam is very important because it's very easy. For me, it's very easy. This is a good chance for you to get 100. Because there's only one solution. If you don't get it, you don't get it. Right? So do a good job in this exam.